Okay, try the next one. Oh, check. Yeah, we'll do check. Great. Okay, try this next one, an actual APQ. Let's see if you can do it. Do not look at your neighbors. Do it all by yourselves.
I'm doing it.
I think the property value is way too high.
I did. I was referring to her to see if I got right. Yeah. Just a daily reminder.
Alrighty. E.
Yes.
E. Yes. Hey, that's good. Okay. Also, I want to point out that all multiple choice questions are not the same length. Some multiple choice questions will take you 5 minutes. This one took you, about 60 seconds now. When you get better, it'll take you like 30 seconds. Yes. Okay. This was okay, right? This was okay. What about this one? No, we're gonna take notes after this. More notes after this. Nope. The next notes is super related to this, so we're gonna keep practicing. Sorry, James.
Last week so much better.
Oh my God, I read.
I gotta learn a lot more last week.
Yeah.
You did just
Okay.
run over it with like.
Okay, guys. You should just. I already know this. I've already answered it.
And then I threw it over.
Yep. A lot of people have already answered it. I'm about to go over the answer, so I need you to try it first. Okay, secant squared is the derivative of tangents. So that's the answer, straight up. Okay? All right, you can read a fun meme.
Don't forget, let's see. Yeah, I was in the first half.
That's pretty funny. Pretty funny. That's pretty funny.
Stop adding me on all these.
Okay.
Once you put on the test, I'm like, I swear, name should be on them.
Okay, can you turn your attention to the next PowerPoint, please?
Or like me rewarding myself after sitting down to do my homework for 2 minutes. These are my stories.
Okay. 4.3. Okay, 4.3, 4.3, 4.3, 4.3.
4.4.
2018.
Yeah, I accidentally printed the date from last
You
year,
understood
so
it.
don't worry about it.
You did really? I'm
Okay.
scared.
Okay, so here are some, okay, so what we just did, Molly, what we just did was called, what we just did was called Leah, can you just, yeah. Yeah. So what we just did was called indefinite integrals. What's an indefinite integral? When there's not numbers here. Okay? These are called the limits of integration. So an indefinite integral has no limits of integration. A definite integral, see how the title of this PowerPoint is definite integration, right? Yeah, see that? Has limits of integration, has numbers, okay? So definite integrals have limits of integration. That's what this PowerPoint is. That's why it's like super similar. We're still integrating all the same things. There's just going to be extra steps at the end because there are limits of integration. So here's 3 properties that have to do with limits of integration. If you're integrating a function from a to b and you reverse the limits of integration, so you're going from b to a, it's going to have the same value, just be the opposite sign.
Wait, what?
If you're going from A to B, but then you want to change it, so you're going from B to A, it's going to have the same value, but the opposite sign. It's going to be the same, but opposite sign.
Oh, I did this con.
Oh. Okay.
No, I kind of just got the hang of it. I didn't know that's what it meant.
Okay. So if you start and end at the same limit of integration, there's one like this in the packet. So like you start at 6, you end at 6, the integral is 0. There's no width, if you're thinking of it as area, there's no width, so the integral is 0 if your limits of integration are equal to each other. Okay, and then this guy, if you have a coefficient, you can just always pull the coefficient out to this side. So let's do some examples of this where I give you this. So I'm telling you, the integral from 1 to 4 is 7, and the integral from 4 to 6 is negative 11. So I can kind of think of this as a number line. So the integral from 1 to 4 is 7, and the integral from 4 to 6 is negative 11. Does anybody want to raise their hand, take a little stab at what do you think the integral from 1 to 6 is? What do you think? Tom?
-4.
I agree. How'd you get that? Does that make sense?
Yeah.
So I'm saying the integral from 1 to 6 is the same as the integral from 1 to 4 plus the integral from 4 to 6. I'm not writing this exactly correctly, but that's the overall idea. Like I should write f of x dx, but you know. Okay. This one would be negative 3 times the integral from 4 to 6 of f of x dx. So it's the same as like, I think you just take my negative 3 and put it on the outside. So just tell me what you think that answer is. Write it on your sheets. On your sheet.
Maybe 12.
All right, Melina, what'd you get and how'd you get it? 33? And how'd you get it?
Well, 4 to 6 is negative 11.
Can you try the next one, what the integral from 4 to 1 is? Please try that. No, I mean from 4 to 1.
Wait, you read it from the bottom to the top?
You always read it from the bottom to the top. What? This is backwards, right? But, ooh, that has to do with it. But you do always read it from the bottom to the top. So it's possible for the bottom to be a bigger number. Mm-hmm. Yep. All right, Gilbert, what'd you get? Negative 7. So if you reverse it, and guys, basically, every single time in the whole wide world you see a bigger number on the bottom, you do want to reverse it. Negative integral from 1 to 4, which would be negative 7. Okay? It's not like your answer is always negative, it always has the opposite sign. I just want to be clear about the negative makes the sign the opposite, not negative. And then do the last one. Do the last one. You got it already? Or do you have a question?
So you're saying because like it's not.
Okay, so what's the last one, Mary Kate?
0.
0. So why is this not always negative, okay? You listening? So let's say I gave you the integral from 6 to 4 for this problem. See how that would be negative 4 to 6? That would be negative 11, which would be 11.
What?
I just want to point out, this doesn't say.
Oh, negative. Yeah. Never mind.
Yes, Melina.
For that, like, would you always, to change the sign, would you always have to know what it was originally?
Yeah.
Okay.
Yep, totally. Okay, so there's a con on this. Checkaroonies. The fundamental theorem of calculus. Does this sound like a big deal?
Yes.
Sort of sounds like a big deal, right? It is. It's called FTC for short. There's going to be 2 versions of the FTC. This is FTC case 1. So maybe we should write that somewhere. Case 1. Yeah, cool. Okay, the fundamental theorem of calculus. Use the fundamental theorem to evaluate definite integrals. The fundamental theorem, okay, here's what it says. So see how f is the antiderivative, capital F is the antiderivative of little f? Yeah. So it just says the integral of little f is big F. See how I'm integrating little f and getting big F, which we've talked about? But the definite part, this is what's new, is you find the integral and you plug in the top limit of integration minus you plug in the bottom limit of integration. So that's what we're going to do with the numbers. Plug in the top minus plug in the bottom.
So that is like another way to get the integral.
So we're still going to integrate the same way we always have. We're just going to have steps on the end where we plug in numbers.
So what is that supposed to give you?
A number? The area under a curve. So you know how we've been using like Riemann sums to approximate areas under curves? So now we're going to be able to, I'll give you a function and I can be like, what's the area between 2 and 6? And you will tell me the exact area. Sweet, this is amazing.
I think we need to do an example.
Yeah, I think we need to do an example. This is not going to be that bad, actually.
Oh, wait, we have to.
Wait,
I'll show you.
Oh.
Wait, go back.
I didn't know.
Okay,
that.
go back. Okay, let's make sure we got it. Yeah, there's stuff to write down. No problem, no problem. Here's kind of like the other thing the FTC says in this process. So see how the derivative of capital F is little f, right?
Yes.
So it's like the derivative, and this is telling you that the derivative and integral are inverse operations. Because like if you're integrating, see how f is a derivative? See how f is a derivative? Yes? So if you integrate a derivative, you get the original. So it's like, think of f, capital F, as the original. So little f is a derivative. If you integrate a derivative, you get the original. So like integrating a derivative cancels and you just get the original.
I thought it was an antiderivative.
What's that?
I thought F like.
It is an antiderivative. So it's like, you know the problems where I was like giving you, like 3x squared? And I told you to think of this as a derivative? Yeah? It's like, I'm like, what's that the derivative of? X cubed, that's the answer. So it's kind of like, if you integrate d dx, the derivative of x cubed, see how like I can make the derivative, instead of writing 3x squared as the derivative of x cubed, right? I'm writing the derivative of 3x of x cubed. But normally I don't write the inside, I don't write the integrand as derivative of x cubed normally. I don't do that. I write it as 3x squared because I know what the derivative of x cubed is. So normally I write what it is. But if I write it, instead of 3x squared, if I write it as the derivative of x cubed, it's like the derivative and the integral cancel out. It's like not that big a deal. You don't need to know this on a high level, but we're just going to compute and do problems and you'll know it from there. Yeah, Melina.
So, how that thing where it's like derivative is going up and
Yeah.
derivative is like, can you do that without I know like which one is like better than
Yeah, that's a great, yes, I love that. Okay, so let's say I have a function f of x, okay? I am going to start, in terms of my first order of operations, I'm going to start by taking its derivative, okay? I get f of x, okay? So that's step one, like step one. So I'm given capital F. My first step is to take its derivative, little f. Then, step two is to integrate little f, and I get capital F.
What's the
So
point?
why
of
do you
that?
do that?
To end up with.
Oh, let's do it with numbers. Yeah, let's do it with numbers. So let's say I'm gonna start with x cubed, okay? I'm gonna derive it, 3x squared, okay? The person who wrote the problem did that for you. And then your problem is what is the integral of 3x squared? And how do we know the integral of 3x squared is x cubed? Because that's like the opposite of a derivative. That's like how we figured that out. So this is step one. Step one, the person doing the problem took the derivative of 3x squared. They were like, it's of x, they took the derivative of x cubed and got 3x squared. And then they gave you the problem, and you're doing like the second step of the problem, and they're like, what's the integral of 3x squared? And you have to be like, let me think backwards. Since this is a derivative, what was the original? It is x cubed.
But I already told it to at the beginning.
Well, normally you don't see this step, right? Like,
So then that would be step one.
I see what you mean. But how do you know the answer to this is x cubed? You know that this is a derivative, and you're asking yourself, what was the original? So like you knew that somebody took the derivative and got it 3x squared, right?
So like you don't actually have to know step one.
No.
What's the next step?
Step one is not right.
But okay. So see how I'm saying this is? I'm glad you're like really trying to like understand this because it's called the fundamental theorem of calculus. So there's going to be a case 2, all right,
Oh no.
where you are going to truly see the 2 steps, and it's going to be you're going to take the integral first and then take the derivative of that.
But then what you started?
And the order of operations will matter. They're both inverse operations. It's gonna always, like a derivative and integral will always cancel out, so to speak. But the order of operations, see how now I'm taking a derivative? Like, see how I'm starting with a derivative? And then I integrate it? So that's case 1. In case 2, when we do it, you're gonna start with an integral and then derive it.
So you're just putting a name to things we've already done.
Yeah.
Okay.
Well, the new part is the plug-in is the numbers, the plugging in the top minus plugging in the bottom. Yeah,
Yeah, okay.
correct. I'm putting a name to what you've already
I feel
done.
like these two is gonna be useless.
Yes,
So
Chris.
then if you have the 3x squared, that's a derivative?
No, the 3x squared is an integral. Like I start with an integral.
I thought you No, it is it's the derivative of
Wait, 3x squared. Oh, yeah, 3x squared is the derivative.
So
Yeah.
then you
Yeah.
integrate it to get the original, and then you have to
Correct.
do it again to get the...
No, you're done.
Just forget it. You had it right the first time.
Okay, let's do this, okay? All right, let's do this. So you're given capital F. Okay, yeah?
You're given the integral.
I'm given the integral, right? So like this is an integral. This is an integral. Okay? I take its derivative. What's the derivative of capital F? Little f. See how they took its derivative for you?
Wait, derivative is capital.
F is little f. The
Would
little
the
the,
integral of
no,
capital F be
the
F?
derivative of big F is little f.
Yes.
Yes. Did I say the opposite? So what is the integral of little, so see how I'm starting with a derivative? See how little f is a derivative? I'm starting with a derivative.
So backwards to think about.
It is backwards. It's totally, I totally get where you're coming
Can you
from.
write it in like the PVA kind of thing so I can see it? Wait,
What?
So I start with f and then I go to little f, deriv. Yep. So I went down a level. I see how I'm starting with big F,
Then you have to integrate to go back.
and then
James, you
I somebody took a derivative and called it little f.
What's got you down, man?
Now I'm going to actually integrate. So what's the integral of little f? Big F, right? So the integral of little f is big F. And then I'm going to plug in the top minus plug in the bottom.
Wait, I already forgot. I'm not.
You look so confused.
Yes. Big F prime is little f.
So where'd you lie? Why would I ask the question? Why do you have to be like a different
James, can you explain it to me? How a derivative is make up a new verb or something.
Let's just start. Let's do some problems. James, yes. Yeah.
James
Okay.
needs a break.
Can you find big F of
Give
4?
me a break, dude.
Can you find big F? Yeah, he always goes on top.
Oh, okay, so you just plugged in those numbers.
Yep.
Wait, so you
We're
don't
doing.
need the derivative?
Not for this problem, you don't.
Wait, hold on. How do you plug in?
Oh god.
Okay, what is f of, big F of 4 is 64 minus 20?
Wait, so put the 4 into the first thing, so you put the 1.
Yeah, I put 4 into big F, which is here.
16 times 1.
So big F of 4 is 4 times 16 minus 5 times 4, which is 64 minus 20, which is 44, right?
Isn't it 43? The answer.
Minus,
Okay.
Oh wait, no.
what's
45.
big F of 1? Okay,
So it's 45.
4 times 1 squared minus 5 times 1. Yeah, you went the opposite way here. 4 minus 5 is negative 1. So 44 minus negative 1, which is 45. That's the answer.
Change my answer.
You want to do the next one?
So what is 45?
The answer.
That's the integral from 1 to 4?
Yeah, of little f.
So that's the area under the curve.
Yes,
So f of 2 minus
of f.
All these words.
Wait, so that's the area underneath the curve of the
Of-
slope
of the
of the
function.
derivative.
Yeah.
Oh, okay. See, yeah.
That's the, so 45 is the area under the curve of the derivative of this. So 45 is the area under the curve of 8x minus 5.
And that's why it's so exact. Because it's almost like
So if I did 8x minus 5, right? Let's do this. Minus 5, bum, 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 bum. Very steep. Very, very steep. From 1, let me make it steeper. From 1 to 5. I'm saying that this area is 45.
Well, why do you want to find the area of the curve under the derivative? Why don't you want to find it of,
Because the derivative
of like the
because the
actual...
derivative is like the slope.
45 is the area
Wait, what?
underneath 8x minus 5. So 45 is the area underneath little f. What's little f? The derivative. Okay, let's.
You're speaking too fast.
So look at my problem. I am starting with a derivative. See how the actual problem I have, this is the derivative I'm starting with? And then I integrate it. So it's that order of operations that's going to be like important. That's the difference between case 1 and case 2 that we'll learn. Yeah,
So you start with the
I don't want to
Yeah.
learn case 2.
You're trying to go back to the
original.
by
So most of the time, okay guys, let me do a problem that we'll be doing 99% of the time. This is 1% of the time, it'll look like this. 99% of the time, you ready? It'll look like 8x minus 5 dx. 99% of the time, you'll be doing this problem. Can we do this problem together?
Where'd you get 8 at?
Sure.
I took the derivative of that.
So you have to integrate it up again?
So what's the derivative? What's the integral of 8x? 4x squared.
Yeah.
What's the integral of 5?
5x.
5x. We'll talk about the plus c in a second. Don't do the plus c. Do you see how we're doing work here? Like, I think you don't like this because there's like not enough that we're doing, right? But 99% of the time you're given this and you integrate. But integration in this context, you want to think of it as like, I'm given the derivative, what was the original? See how this is the derivative and you're playing the game of like, what was the original? But you might be playing the game of like, add 1 to the exponent, divide by new exponent. That's just the trick. The concept is this is a derivative, this was the original. From, okay, and then you plug in and then you say like, now you know, from 1 to 4, and then you plug in and you would get like 44 minus negative 1 is 45, okay?
Okay.
So when I say this is a derivative, you might be like, Michelle's, I just think of this as a regular function and I'm going to add 1 to the exponent, divide by new exponent. That's fine, but conceptually, this is the derivative and you say, what's the antiderivative? This. Okay, so what's the antiderivative of little g? Big G. Check.
Big G.
And then you plug in the top minus plug in the bottom.
Did you get 14?
Well, don't give it away. I want everybody to do it.
I thought we were going to do that.
So do this out, please.
Oh, no.
14.
Wait, so it's like this.
Telling you I have the four.
James, man. James, James, you understand this?
What?
I think he's tripping.
He's watching Denzel play with chopsticks.
Yes. Yep.
Cool.
Okay, how's this? Height? Is this okay? Okay, let's do,
That's really just it.
all right, let's do another problem, okay? Let's do another problem. You ready for another problem? What's the so 2x, and I'm not going to ask what's the integral of 2x. I'm going to say 2x is the derivative. It's the derivative of what? What's 2x the derivative of?
X squared.
X squared. Okay? So see how I said I'm given a derivative first. This is the derivative of what? X squared. Plus c. Should we talk about the plus c at this point? All right, let's talk about the plus c. Because so far we haven't been doing plus c's, but why not? Like, we've been doing plus c's. So let's put in the plus c. See what happens, okay? Plus c. Now, I need to indicate that I'm going from 3 to 4, right? Guys, stay with me. New notation alert, new notation alert. I need to indicate that I'm going from 3 to 4, but I can't write them there because I've already taken the integral, so I don't want to write an integral sign, right? So I'm just going to put them here in the end with a vertical line, just a straight up vertical line from 3 to 4, to keep track of the fact that I have a 3 and a 4, okay?
Is this like AP Junior presentation?
Yes, of course. Why would I teach you anything else? I'm not teaching you like Ms. Sheld's calculus. I'm teaching you like that calculus that everybody
Technically it
does.
is.
Yeah.
Some teachers back in the day, they be tripping.
Okay. You ready to plug in? Are you ready to plug in?
Explain.
I'm going to plug in 4. So I get 16 plus c when I plug in 4, right?
You have to keep this.
Minus. You ready to plug in the 3? 9 plus c when I plug in the 3.
Oh, the C's just cancel out.
The c's just cancel out.
Creamed our love because through the
I'm
principal
so
ball.
sorry, Michelle's.
You lost.
I do have Mary Kay Gaffney. Okay.
Bye.
So 16, guys, I'm just going to show this out. 16 plus c minus 9 minus c. Check. What happens to the c's? They cancel. So I can just get 7.
Let's go.
Why are they like so important?
Yeah.
Well, the C's always cancel.
They will always cancel for a definite integral. Do you see how like you'd always have a c for the first part and a c for the second part, and you're always going to subtract? Because that's the fundamental theorem of calculus, is plug in top minus plug in the bottom. So the c's will always cancel. So this is one of the differences, alert, alert, between an indefinite integral. So indefinite integral, in-def integral. There's no numbers here, no numbers, okay? And you would need a plus c. It doesn't cancel. You need a plus c. Just remember the derivative of a constant goes away. So there could have been any constant, and the derivative would have been the same. If you're adding a plus 7, a plus 10, the derivative would be like the same. So for a definite integral, these have numbers, and the plus c's will always cancel. Do you see how like they would always? Do you see why like it would cancel?
But couldn't they be any random number?
But it would be the same for each one. Like the integral of this is going to be a certain number.
Oh no.
Yeah, but
So this would be like 7. It's not going to be a 7 here and a 20 there,
oh, okay.
right? It would always be the same certain number. So you don't need plus c. Don't need plus c. Also, while we're summarizing, guys, the difference between indefinite and definite. An indefinite integral, the answer is going to be a function, like variables. The answer is a function. Here the answer is a number. Okay? Okay, so let's do the second one. Let's do it together still. So I'm not going to put the plus c's because it's a definite integral and I know they'll cancel out. So the integral of 2x to the 4th would be 2/5 x to the 5th. Is this good so far?
Mm-hmm.
So I'm saying like 2x to the 4th is the derivative of 2/5 x to the 5th. Minus 3x squared is the derivative of what?
X cubed.
X cubed. Thank you, Eric. I need to keep track of my numbers, so I'll do the vertical line -1 to 1. Be very careful. What's that? So if I kept this, I've lost my numbers. I just need to keep track of them.
You have fifth period.
Yeah. It's to say like they didn't go away. But I can't write them in front of an integral anymore because I have integrated. Yeah. So it is just a show. All right, you ready to plug in together?
That feels weird.
2/5 times 1 to the 5th minus 1 to the 3rd minus, mistake alert, when there's multiple terms after a minus sign, you're going to need to distribute. So always put parentheses after this minus sign. Otherwise, you'll make a mistake. Does that make sense?
Yeah.
Because this is multiple terms. When you're subtracting multiple terms, you'll need to distribute. If you don't do the parentheses, you won't distribute. Problem. So 2/5 -1 to the 5th minus -1 to the 3rd. See how there's a lot of opportunities for mistakes here. So I plugged in the top. This is me plugging in the top number. This is me plugging in the bottom number. So this is like my f of b minus f of a. Yeah, what's up?
Did you read if he's correct?
I haven't done it out yet. This is the same number.
There's just so many different functions, like I don't know which one to use.
I just did it.
You get the same number each time, so this is probably right.
Okay.
Yeah.
That is like interesting.
Yeah, do it out. I want you to actually like give me the final number. I want you to do it out. Yeah.
Oh, sorry. Yeah.
You're doing the and
Yeah.
You're doing what we've been doing for like the last 2 days. Well, there's 2 ways to go. You say 2x or you just use your rules where you say add 1 to the exponent, 2x divided by 2x divided by 2.
41, I think it's dropped.
We're doing like the add 1 to the exponent divided by 2.
So
Yeah. Yeah, you integrate. This thing is called integrate. Yeah. Yes. Okay, let's do this out. Let's do this out. So 2/5 minus 1 minus 2 minus plus 1. Is this okay?
Yeah.
Yeah? So some people would simplify within the parentheses first. I would not. See how these are going to have common denominators? So I would suggest distributing rather than doing the parentheses first. I know Pem does all like parentheses first, but you can distribute. So I just do like 2/5 minus 1, distribute, plus 2/5 minus 1. Do you see me distributing? It's just going to be like nicer on the fractions if you do it that way. 2/5 and 2/5 is 4/5. -1 and -1 is -2. negative 6/5 or negative 1 1/5? We're gonna work on this for like a week. Just to let you know also.
Might need like
The classwork on this is like miles long. So, you want it? Yeah, sure. I haven't printed it out yet, but yeah. Okay? Preguntas, questions?
Always forget. Need to do the classic.
All right, let's do this one. Try it all on your own.
I can't, sorry.
I think it's 31.
No, we have plenty. This is our closing question. This is our exit ticket right here. Okay?
Oh my god, they're actually not missing. Ew.
Oh, we always have like
Right?
Michelle.
Dude, we probably should, we should not be counting, we can't figure out
We had to
where
like
the
get
last
like.
is gonna be.
So you're saying 3x to the 4.
Yeah, there's a 500,000. So it's either 30 or 39. So you're like,
Wait, so where does this see?
all you need is watch a movie.
From what I got here.
Yeah, correct. You plug in a 2 to look at them. And then you do a 9. And then you plug in a 1.
And then
So you plug in the top one is what happens.
What are they doing?
$32. 32 times 3 is 96.
96 divided by 5.
Correct.
So that could be. Wait. So would I have to plug in both and then?
Yeah, like you plug in 2 to both of these terms. Yeah, so plug in 2 to the x squared over 2 as well before you keep going.
It's about 2.
Keep going. Keep going.
110.
Keep going. Keep going.
What's after the -2?
Minus 3/5 plus a half.
What's 86 times 2?
Oh, we didn't get the final answer. I guess we'll have to get it tomorrow. Okay, so definite integration will not be on tomorrow's Do Now quiz. Indefinite integration, like without the numbers, will be. Got it? With rational exponents, fractional exponents, like negatives, you know? So beware of that.